The Big Bang Paradox. The universe, as we know it, began with the Big Bang, a colossal eruption from an unimaginably dense singularity, expanding space, time, and matter into existence. But this leads to an unsettling question. What came before? If time itself started with the Big Bang, can before even exist? The paradox deepens when we ask why it happened at all. Some theories suggest a quantum fluctuation triggered it, a random spark from nothingness. But how can nothing create something? Others propose a cyclic universe, endlessly rebirthing after each collapse. Yet even that implies an original beginning. Perhaps we're part of a multiverse, one bubble among infinite others, but that only shifts the mystery to an even grander scale. What birthed the multiverse? This paradox forces us to confront the limits of human understanding, blurring the line between physics and philosophy. Was there ever truly nothing, or has something always existed? The fine-tuning paradox. The universe appears eerily calibrated for life. Physical constants, gravity, electromagnetism, nuclear forces, are so precisely balanced that even a microscopic change would render life impossible. If gravity were slightly stronger, stars would burn out too fast. Weaker, and they'd never ignite. Why is the universe tuned so perfectly? One explanation suggests an infinite number of universes exist, each with random settings, and we simply live in the lucky one. Another idea entertains intelligent design, that such precision implies a creator. Yet the paradox remains. Is our universe special, or just an improbable accident? The Anthropic Paradox. We observe a universe perfectly suited for life, but is that because it's the only kind of universe we could observe? The Anthropic Paradox suggests the universe appears tailored for life not because it was designed that way, but because if it weren't, we wouldn't be here to notice. It raises a profound question. Is the universe truly fine-tuned for us? Or are we simply a byproduct of an inevitable, indifferent cosmos? The Simulation Paradox. What if everything, from the stars to your own consciousness, is part of an advanced simulation? This paradox emerges from the idea that if civilizations ever become powerful enough to simulate worlds, they'd likely create countless simulations. Statistically, it becomes more probable that we're in one of those simulations than in the original, base reality. Are we digital beings, unaware of the code that binds us? If so, how could we ever tell the difference? The Fermi Paradox. With billions of galaxies, stars, and potentially habitable planets, intelligent life should be abundant. Yet the universe remains silent. This is the heart of the Fermi Paradox. Where is everyone? One possibility is that advanced civilizations self-destruct before spreading among the stars. Another idea proposes that they're deliberately avoiding us, or perhaps we're too primitive to notice them. A darker thought. Maybe we're alone, an anomaly in a vast, empty cosmos. The Great Filter Paradox. If life's ingredients are common, why don't we see advanced civilizations? The Great Filter Paradox suggests a near-impossible barrier. The filter exists somewhere in the timeline of life's evolution. Could be behind us, meaning we're incredibly rare survivors, or it could be ahead, implying civilization's inevitable extinction. The unsettling part? If we find primitive life elsewhere, it might mean the filter still waits for us. The Heat-Death Paradox. Entropy, the gradual decline into disorder, increases relentlessly. Eventually, stars will burn out, black holes will evaporate, and the universe may become a cold, dark void where no energy flows. But why hasn't this already happened if the universe is so old? Is entropy reset somehow? Or are we witnessing a brief, vibrant moment in an otherwise dying cosmos? The Heat-Death Paradox reminds us that even the universe isn't eternal, or is it? The Multiverse Observability Paradox. The multiverse theory proposes infinite universes, each with different physical laws. But if other universes exist, why can't we observe them? The paradox lies in the contradiction. If the multiverse is real, shouldn't there be some trace of these alternate realities? Or is our universe uniquely isolated, forever cut off from the rest? Olbers Paradox. In an infinite universe filled with infinite stars, why isn't the night sky ablaze with endless light? Olbers Paradox argues that even the most distant star's light should eventually reach us. Yet space remains dark. The answer might lie in the universe's expansion, which stretches light into invisible wavelengths, or perhaps the cosmos simply isn't infinite. Either way, the darkness is a paradox waiting to be illuminated. The Cosmological Horizon Paradox. The observable universe has a limit, the distance light has traveled since the Big Bang. But distant regions of the cosmos, separated by vast gaps and no causal contact, somehow look remarkably similar in temperature and structure. This Cosmological Horizon Paradox suggests they once communicated faster than light allows, a contradiction in physics. Did an unknown force, or perhaps inflation, synchronize the universe before time itself began? The Information Paradox. Black holes consume everything that crosses their event horizon. Matter, light, even information itself. But what happens to that information? Quantum physics insists that information cannot be destroyed, yet black holes seem to do just that. This contradiction, known as the Information Paradox, pits two of physics' most powerful theories, quantum mechanics and general relativity, against each other. Stephen Hawking proposed that black holes emit radiation, slowly evaporating over time. But when a black hole disappears, where does the information it swallowed go? Is it lost forever, breaking quantum laws? Or does it somehow escape through the radiation, encoded in a form we can't yet understand? Some theorists suggest information gets imprinted on the event horizon itself, a concept tied to the holographic principle, where our three-dimensional reality could be a projection from a two-dimensional surface. Others speculate that black holes might connect to parallel universes, dumping information elsewhere. The truth remains hidden, locked behind the most mysterious objects in the cosmos. The Twin Paradox. Imagine two twins. One stays on Earth while the other travels through space at near-light speed. When the traveling twin returns, they've aged significantly less than the twin who stayed home. This is the Twin Paradox, born from Einstein's theory of relativity. Time isn't absolute. It stretches and contracts depending on speed and gravity. From the traveling twins' perspective, they experienced a short, quick trip. But for the earthbound twin, decades may have passed. The paradox challenges our intuitive sense of time, forcing us to accept that time is flexible, not fixed. It's a reminder that the faster we move through space, the slower we move through time, a mind-bending consequence of the universe's very fabric. The White Hole Paradox. If black holes pull everything in, could their opposite, white holes, push everything out? A white hole would be a region of space-time that nothing can enter, only exit. The equations of general relativity allow for them, but none have been observed. Some speculate that black holes might connect to white holes, creating a cosmic tunnel, a wormhole, bridging distant parts of the universe. Others propose that the Big Bang itself might have been a massive white hole, ejecting all matter and energy into existence. The paradox lies in their apparent non-existence, despite the math saying they should be there. Are white holes hiding from us, or do they defy reality in a way we haven't yet grasped? The Quantum Entanglement Paradox. Two particles, once entangled, remain mysteriously connected, no matter how far apart they drift. Measuring one particle instantly affects the other, faster than the speed of light. Einstein called this spooky action at a distance, and it's still one of quantum physics' strangest puzzles. How do particles communicate across vast distances with no signal in between? Some believe this hints at hidden variables, unseen layers of reality beyond our current understanding. Others propose that entangled particles aren't sending information at all. They share a deeper, quantum connection that transcends space-time. The paradox exposes a reality where distance and time may not matter, a universe more interconnected than we ever imagined. The dark matter paradox. Galaxies spin too fast. Their outer stars should fly off into space. Yet they hold together as though held by an invisible force. This is the dark matter paradox. Calculations suggest most of the universe's mass is made of this unseen substance, yet we've never detected it directly. It doesn't emit, absorb, or reflect light. It's utterly invisible. So what is it? Some theories propose exotic particles like WIMPs, weakly interacting massive particles, or axions. Others suggest gravity itself might behave differently on cosmic scales. If dark matter isn't real, then our understanding of the universe's structure is fundamentally flawed. The dark energy paradox. Not only is the universe expanding, it's accelerating. Something unknown, dubbed dark energy, drives this expansion. But what is dark energy? It accounts for roughly 68% of the universe's energy content, yet remains completely mysterious. Is it a property of space itself? A new, undiscovered force? Or a sign that our equations about gravity and the cosmos are incomplete? The paradox deepens because this acceleration should eventually pull galaxies so far apart that even light won't connect them, leaving an empty, silent universe. The Baryon Asymmetry Paradox. The universe shouldn't exist, at least not the way we know it. The Big Bang should have created equal amounts of matter and antimatter, which should have annihilated each other entirely. But somehow matter won. This is the Baryon Asymmetry Paradox. Why is there more matter than antimatter? The imbalance is slight. For every billion antimatter particles, 1,000,000,001 matter particles emerged. That tiny leftover matter formed everything: stars, planets, and us. But no theory fully explains why this imbalance occurred. The Hubble tension paradox. The universe's expansion rate, described by the Hubble constant, should be the same no matter how we measure it. Yet different methods give conflicting results. This is the Hubble tension paradox. One approach, based on the cosmic microwave background, gives a slower rate. Another, using supernovae, shows a faster one. Both can't be right. The tension hints at a major gap in our understanding of the universe's history and composition. The Flatness Paradox. The universe appears geometrically flat, parallel lines never meet, and cosmic microwave background radiation supports this. But why? For the universe to be this precisely flat, its early conditions had to be unbelievably fine-tuned. Any slight curvature should have grown dramatically over billions of years. Inflation theory tries to explain it, proposing a rapid, early expansion smoothed everything out. Yet even that leaves us asking why the universe's initial conditions were so perfectly balanced. The missing Baryon Paradox. We can only see about 5% of the universe, the rest is dark matter and dark energy. But even that visible 5% seems incomplete. Simulations predict more ordinary matter than we can find, a mystery called the missing Baryon Paradox. Some of this missing matter might exist as hot, diffuse gas in intergalactic space, but so far, it remains elusive. Where is the universe hiding its lost matter? The cold spot paradox. The universe's microwave background radiation, the afterglow of the Big Bang, is remarkably uniform, but one enormous, chilling anomaly stands out: the cold spot. This vast region, about 1.8 billion light-years across, is significantly colder than the surrounding space. Theories swirl around it. Some suggest it's a supervoid, a massive empty region with less matter. Others hint at something stranger, perhaps a collision with another universe in a multiverse landscape. The cold spot shouldn't exist based on our current cosmological models, and its presence might point to a deeper, hidden reality beyond our own. The axis of evil paradox. Cosmic microwave background radiation should appear random and uniform in all directions. Yet, it seems oddly aligned with our solar system, a pattern scientists jokingly call the axis of evil. This alignment defies statistical expectations and undermines the idea that the universe has no preferred direction. Is it an observational glitch? A bizarre coincidence? Or could it suggest our universe has an intrinsic structure we don't yet understand? The paradox remains unsolved, leaving scientists uneasy about whether we truly understand the cosmic blueprint. The quantum foam paradox. Zoom in far enough to the Planck scale, and space-time itself becomes turbulent and chaotic like a foamy sea. This quantum foam should cause tiny, unpredictable fluctuations. However, the universe appears remarkably smooth and stable at large scales. How does this foamy, chaotic foundation give rise to such an orderly cosmos? The paradox suggests there's a missing link between quantum mechanics and general relativity, two pillars of physics that refuse to fully cooperate. The Big Rip Paradox. Dark energy is driving the universe's expansion, but what if it doesn't stop? The Big Rip proposes that this acceleration might eventually grow so powerful that it tears galaxies, stars, planets, and even atoms apart. In this catastrophic endgame, space-time itself could unravel. The paradox? We have no clear understanding of dark energy's nature, or whether it will stay constant, fade, or intensify. If the Big Rip is real, everything, even the very fabric of reality, could have an expiration date. The Bootstrap Paradox. Imagine an object, a piece of knowledge, or even a person that exists without an origin. For example, what if a time traveler gives Shakespeare a copy of his plays, and Shakespeare merely copies them? Who really wrote them? This is the Bootstrap Paradox. An object or information trapped in an eternal loop, never created, yet always existing. It's a mind-twisting consequence of time travel theories, where cause and effect become tangled beyond recognition. The paradox raises a haunting question. Can something exist without a beginning? The Cosmic Coincidence Paradox. Dark matter and dark energy dominate the universe, yet right now, in this very era, their effects seem perfectly balanced with ordinary matter to shape galaxies and cosmic structures. This balance seems too coincidental. Why now? Why us? If dark energy's strength changes over time, we could be living in an exceptionally rare moment where this equilibrium allows life to exist. Some physicists argue it's pure luck. Others think it hints at a deeper cosmic design or even a multiverse where countless other universes play out differently. The Lithium Abundance Paradox. The Big Bang produced hydrogen, helium, and a trace of lithium. Yet, when astronomers measure the lithium content in old stars, it's 3 times less than what theories predict. This discrepancy, known as the Lithium Abundance Paradox, suggests either our understanding of nuclear processes in the early universe is flawed or something altered the lithium afterward. Did stars destroy it? Did unknown particles interfere with its creation? Or is an undiscovered aspect of physics reshaping our cosmic chemistry? The Early Galaxy Formation Paradox. Galaxies shouldn't have formed as quickly as they did after the Big Bang, yet telescopes reveal massive, mature galaxies in the early universe. How did they grow so fast? This paradox challenges models of star formation and galaxy evolution. Some propose dark matter accelerated their growth, while others suspect our understanding of the young universe is incomplete. The paradox hints at a rapid, chaotic cosmic infancy we barely comprehend. The Magnetic Monopole Paradox. Magnets always have 2 poles, north and south. Yet physics predicts the existence of magnetic monopoles. particles with only one magnetic charge. Despite decades of searching, none have been found. If they exist, monopoles could explain why electric charge is quantized, why electrons have exactly the same charge. Their absence leaves physicists baffled. Did the early universe somehow suppress monopoles? Or is there a deeper, hidden symmetry we've yet to uncover? The Redshift-Distance Paradox. Redshift measures how fast galaxies move away from us, a key tool in calculating cosmic distances. But some quasars, intensely bright objects at the edge of the universe, appear connected to galaxies with vastly different redshifts. If they're connected, they should be at the same distance, but their redshifts say otherwise. This paradox challenges whether redshift always equates to distance. Could it point to new physics or exotic phenomena, like cosmic strings or alternate dimensions? The Dark Flow Paradox. Galaxies should move in random directions, driven by local gravity and cosmic expansion. Yet astronomers discovered a strange, consistent motion. Galaxy clusters drifting toward an unexplained point beyond our observable universe. This dark flow defies expectations. Is it a gravitational pull from a massive structure outside our cosmic horizon? Perhaps another universe? Or is it a flaw in our understanding of space-time? The paradox teases the idea that our universe may be just one part of a larger, unseen cosmic landscape. The Reionization Paradox. After the Big Bang, the universe cooled into a dark, neutral fog. Hundreds of millions of years later, something, possibly the first stars or black holes, reionized the universe, making it transparent again. But this process seems to have happened faster than current models predict. How could early galaxies form so quickly and emit enough energy to reionize the cosmos? The paradox suggests either unknown physics or an overlooked cosmic event radically accelerated this transformation. The Supermassive Black Hole Paradox. Supermassive black holes, billions of times more massive than our Sun, existed surprisingly early in the universe. Growing a black hole that large should take far longer than the age of the universe at the time they're observed. How did they form so fast? Did they start from colossal seed black holes, or did some unknown rapid growth mechanism kick in? This paradox hints at missing pieces in our understanding of black hole physics and early cosmic evolution. The Galaxy Rotation Paradox. Galaxies spin faster than they should. Based on visible matter, their outer stars should be flung into space. Yet they stay intact, rotating as if held together by invisible mass. This led to the theory of dark matter, but decades later, we still can't detect it directly. Could an alternative theory of gravity explain the anomaly? Or is dark matter simply more elusive than we imagine? The paradox remains one of modern astronomy's biggest mysteries. The Cosmic Neutrino Background Paradox. Just as the cosmic microwave background is the Big Bang's leftover light, the universe should also be filled with a neutrino background, ghostly particles from the earliest moments of creation. Physics predicts their existence, yet we've never detected them. Are our detectors not sensitive enough? Or is something blocking them? This paradox raises the possibility that the early universe's physics is stranger than we think, or that neutrinos themselves hold secrets beyond current science. The ultra-high-energy cosmic ray paradox. Cosmic rays, high-energy particles from space, hit Earth all the time. But some come with absurdly high energy, beyond what known astrophysical processes can produce. These ultra-high-energy cosmic rays shouldn't exist according to current physics, yet they do. Are they propelled by unknown cosmic phenomena, or do they come from beyond our observable universe? The paradox hints at undiscovered forces or even exotic objects like decaying dark matter particles. The Missing Satellite Paradox. Simulations of dark matter predict that galaxies like the Milky Way should have hundreds of tiny satellite galaxies orbiting them. Yet we only observe a fraction of that number. Where are the missing galaxies? Did they form invisibly, made purely of dark matter, or did they never form at all? The paradox implies that either dark matter behaves differently than we assume, or galaxy formation is more complex than our best models predict. The Quasar Alignment Paradox. Quasars, some of the brightest objects in the universe, should be randomly oriented across the cosmos. Yet astronomers discovered large groups of quasars whose spins are mysteriously aligned over billions of light years. This baffling pattern violates expectations of randomness and isotropy. Could an unknown cosmic force or large-scale structure be influencing their alignment? The paradox pushes the limits of what we know about the universe's large-scale organization. The Time-Asymmetry Paradox. Why does time flow in one direction, from past to future, while physics equations work perfectly fine in reverse? The universe began in an incredibly low entropy state, but why? If entropy must always increase, how did the universe start off so improbably ordered? The Time-Asymmetry Paradox hints that something extraordinary happened at the Big Bang, setting the arrow of time in motion, yet no one knows why time refuses to rewind. The Planck Scale Paradox. The Planck scale is the universe's smallest, most fundamental level, where space and time themselves blur into quantum uncertainty. At this scale, gravity and quantum mechanics collide, creating a realm where both theories break down. Why doesn't this chaos ripple upward into the large-scale, smooth universe we observe? The paradox suggests that an undiscovered theory, a theory of everything, must exist to unify quantum physics and relativity, yet we haven't found it. The Multiverse Observability Paradox. If a multiverse exists, countless other universes with different laws of physics, why can't we detect any signs of them? Some theories suggest these alternate realities may be forever out of reach, separated by cosmic barriers we can never cross. Yet other models hint that subtle imprints, like strange alignments in the cosmic microwave background or unexplained quantum phenomena, could be shadows of neighboring universes. The paradox lies in whether we live in an isolated cosmos or are part of a vast, unseen multiversal web, and if so, why can't we prove it? The White Hole Paradox. If black holes devour everything, their theoretical counterpart, white holes, should spew matter and light outward, preventing anything from entering. Yet no one has ever observed one. Are they purely mathematical curiosities? Or could they exist in hidden corners of the cosmos? Some physicists propose that white holes might form when black holes die, or that they could even be connected to wormholes. The paradox leaves a tantalizing question. Are white holes a reality we simply haven't found yet, or a misstep in our understanding of space-time? The Vacuum-Decay Paradox. What if the universe isn't truly stable? Quantum mechanics suggests we might live in a false vacuum, a temporary, less stable state of reality. A random quantum event could trigger vacuum decay, collapsing the universe into a lower-energy true vacuum at the speed of light, rewriting the laws of physics in an instant. The paradox lies in why this hasn't happened yet, and whether it ever will. Are we incredibly lucky, or is there something deeper protecting our universe from such a sudden, catastrophic end? The Antimatter Paradox. The Big Bang should have created equal amounts of matter and antimatter, yet the universe is dominated by matter. Antimatter, which annihilates normal matter upon contact, seems to be mysteriously absent. Why? Some theories propose subtle differences in particle behavior, CP violation, tipped the balance, while others hint at hidden antimatter galaxies. The paradox touches on the very nature of existence. If antimatter had won instead, we might not be here to ask the question. The Information Paradox. Black holes are notorious for swallowing everything, even information. According to classical physics, anything that falls into a black hole is lost forever. Yet quantum mechanics insists information can't be destroyed. This paradox pits two pillars of physics against each other. Recent breakthroughs suggest Hawking radiation might encode information as a black hole evaporates, but how that works remains a mystery. Does information escape in a scrambled form, or is it lost to another universe? The fine-tuning paradox. The universe's physical constants, from gravity's strength to the charge of an electron, seem precisely balanced to allow life. Even slight changes would make stars, planets, and life impossible. Is this an extraordinary coincidence, a sign of intelligent design, or evidence of a vast multiverse where countless universes exist with different physical laws? The fine-tuning paradox leaves us wondering whether we're impossibly lucky or part of a larger, mind-bending reality. The Great Filter Paradox. If intelligent life can arise and expand through the cosmos, why haven't we found any evidence of advanced civilizations? The Great Filter suggests a catastrophic barrier might prevent life from reaching that stage. The chilling part? We don't know if the filter is behind us, meaning we're rare survivors, or ahead of us, implying civilization's doom is inevitable. The paradox forces us to ask, are we early, lucky, or doomed? The horizon problem. Distant regions of the universe have identical temperatures and properties, despite being too far apart to ever exchange light or energy. This defies the idea that information can't travel faster than light. Inflation theory proposes the universe expanded faster than light for a brief moment after the Big Bang, connecting these regions, but the mechanics remain unproven. The paradox hints at hidden physics in the universe's earliest moments. The Baryon Asymmetry Paradox. Baryons, the particles making up atoms, should exist in equal amounts of matter and antimatter after the Big Bang. Yet, for reasons we don't understand, matter vastly outnumbers antimatter. This imbalance is why stars, planets, and people exist. Physicists hunt for clues in particle physics, but so far, the asymmetry remains a cosmic riddle. Why does the universe favor matter? Without this imbalance, the universe might have been a barren void. The missing Baryon paradox. Even after accounting for dark matter and energy, half of the ordinary matter baryons predicted by Big Bang models is missing from the observable universe. Recent studies suggest it might be hiding in diffuse, hot intergalactic gas, but detection remains tricky. If the missing matter isn't found, it would mean our understanding of the universe's composition is fundamentally flawed. Where did all this missing matter go? The Quantum Entanglement Paradox. Two particles can become entangled, sharing a connection that lets them influence each other instantly, no matter how far apart they are. This spooky action at a distance, as Einstein called it, seems to defy the universal speed limit, the speed of light. Yet, experiments confirm entanglement is real. The paradox raises profound questions about reality itself. Is information traveling faster than light, or is space-time interconnected in